So today I'd like to tell you about work that I've been doing during my time at Google, trying to build theoretical foundations for deep learning more from the perspective of physics. So today I'd like to tell you about work that I've been doing during my time at Google. A little bit of echo. Is that natural? Now it's gone. Okay, maybe it'll just okay. So we've all heard about amazing achievements from the past few years from machine learning, and now more so getting closer to AI and kind of general systems that can solve computational problems. And behind all this, there are a few core features, but one of those is the fact that all of them rely on deep neural networks as the flexible model that is doing the learning. And a common view, I think, in this area in machine learning is that deep neural networks are just a black box and they will remain that way. It's pretty hard to understand anything about them that's scientifically accurate and pretty robust and maybe even predictive. And this core challenge originates just from the complexity of neural networks as a model. I'm going to try to convince you that we don't have to keep it fully at a black box level. There are certain things about them that we can understand. And I'll try to give some highlights from some of my work over time on this question. But I think maybe formalizing it into a more central question that is interesting from a physics perspective is to understand how learning and computation emerge from collective dynamics and interactions of simple processing elements. So stated in this view, it has a little bit more of a relationship with other places where physicists study a many-body problem. This particular problem is classical, but I want to kind of give a little bit of a flavor of how really you can take this point of view and make a little bit of progress overall on this problem. I would say that particularly for physics, we would like to not just use off-the-shelf methods from machine learning when we apply it to our work, but it would be satisfying to understand some deeper principles and potentially formulate new methods accordingly in the future. And maybe just to give a little bit of a historical footnote, to kind of the present time in machine learning and AI, I think there were a lot of folk wisdoms from past decades and even mathematically rigorous theory that led to potentially kind of somewhat inaccurate conclusions, or maybe not quite the right picture for practice in terms of what neural networks are capable of, what their optimization is like, what the landscape of neural networks is like, and just what is possible with these models when you learn from data. And that kind of brings us to this current era, which is very experimentally driven, really driven by the fact that people try out many different things and find build systems that work very well empirically. So in this talk, I want to focus on a few questions and try to answer them. So can we say anything about what deep neural networks actually learn? To what extent can we understand this problem theoretically? Are there simple models of learning dynamics that are predictive and can give us some insight? And towards the end, I'll talk about how we can use some of these models that I derived earlier in the talk to understand one particular problem, which is looking at the way that error after learning or training scales with some basic variables in the problem. When I talk about theories of learning from the perspective of physics, I really mean all sorts of drawing from all sorts of aspects of physics, so both ideas, theoretical tools, and just the general scientific methodology where we have some theory, but we also give a lot of credence to experiment in terms of what is actually observed. And if you're interested, we recently organized just this past winter a KITP program on this topic. Before I dive into that, I want to just highlight a few kind of more from a scientific angle questions that one can formulate around principles of learning and computation more from this perspective of physics. So there many of the optimization landscapes that we deal with when we use neural networks for some learning problem are formally non-convex and they're high dimensional. What we understand now is that they often have critical points that are saddle points at higher values of the loss or the energy. But we still don't understand why this arises, what aspects of the data or the architecture give rise to this. With respect to the dynamics of learning, so there is this landscape that we can study globally, but learning takes a very specific trajectory through the landscape. So what is that trajectory? Can we say anything about it when we run a simple algorithm? We don't quite understand in kind of simple principles what role data plays. So if real data is hierarchical and has particular properties, how does that shape both these other aspects of the problem? I think it's also fruitful to take an information theoretic point of view on the problem and think about information flow through neural networks. And then more recently in large scale systems, there are these conversations around understanding new abilities on new problems that emerge with scale. So as we scale up neural networks with more data and we increase the model size, we find kind of general problem-solving ability emerge, even though the network may not have seen a particular type of problem during the course of training. And so understanding that kind of emergence, and there are conversations about that in the research community. So the outline for my talk is that I'd first like to start off by describing Gaussian theories of neural networks that we worked on quite a bit. There are some exact correspondences that you can build between neural networks and Gaussian theories that were new and gave rise to new methods and new insights. Then I want to talk about one particular way of solving for the dynamics of learning, in which essentially you get a linear model, a very simple model that emerges when you scale up some dimension in the problem, and also how we can capture some sharp dynamical transitions away from these types of models as we tune a particular parameter. And then towards the end, I'll talk about just one application of these types of models in understanding a particular kind of more practically relevant problem in machine learning, which is to understand how the error after training scales. So questions around sample complexity of different models and how we can get insights from this prior work to work on that problem. So just so we're on the same page, let me just define a vanilla fully connected deep neural network. So a deep neural network typically has a depth L to its computation and a width N in the size of the hidden layer. So here in this cartoon picture, there's a depth L. N is the number of hidden nodes in each of the layers. I'm going to take it to be uniform in this model. And the neural network, in this vanilla setting, basically computes a recursion from the input to the output. So what comes in is some input X, which is a vector in RD, for example. I apply some weights, a linear transformation and a shift to it, and I pass it through a nonlinearity phi to produce kind of outputs right after the hidden node. And I repeat this process, order L times for a depth L network. But it's encapsulated by this core computation, which involves both linear transformations and shifts, as well as the application of pointwise nonlinearities. So one of the things that was observed a few years back, which motivated some of our work, was the following empirical observations that were getting a lot of focus in the community, which was that if you look at the error after learning, either for the training set or in some new fresh data. So this is the test set or the population error. You see that as you increase this hidden layer with n, the test error, which is the quantity you're really interested in, improves what looks to be monotonically as you increase n. Even past the point where you've fit the problem perfectly on the training data. So that's where this blue curve just hits 0. And there was kind of a folk wisdom around Occam's razor in the machine learning community, where they tend to interpret the best model as one which fits the data with the fewest parameters. So they think of kind of complexity being measured in terms of number of parameters. But here we have models that have large numbers of parameters. We can keep increasing n, and we see good values for the test error. So
is that the error or the loss?
So here it's probably just loss. You're asking whether it's like a regression problem or classification?
Well, I mean, the reason I ask is because you can, on the training set, you can get 0 error, but you can continue reducing the loss if you're using some cross entropy because you're even more certain. And so, the fact that the curve looks flat from 32 to 8K doesn't necessarily mean there's nothing going on.
This might have been for a quadratic loss, for a square loss. So I actually don't remember if it was cross entropy or it was just regression with a quadratic loss.
In any event, it's so surprising that the test error doesn't go up from overfitting. I think that's the point.
Yeah, that is one of the main points. It's missing. So depending on what kind of data you have, you might have some double descent behavior and so on in between. But once you get past that, you just tend to see kind of nice, smooth improvements. And also it appears to be converging to something. So you might ask, or at least we asked, is there a description of this problem to which it's converging? So is there an infinite width theory where we take n to infinity that describes this problem? So to talk a little bit about that, so what happens to neural networks in this large n limit? We want to start by thinking about random networks, because any kind of learning procedure, whether we have some Bayesian framework that I'm going to talk about or some optimization-based framework, we still start with random networks before we train. So we draw these neural network parameters randomly from some prior distribution. Typically, they're drawn IID from simple distributions, but crucially, they tend to have a particular scaling. So just as an example, if we have weights and biases in this vanilla network, the variance of the weights in practice is scaled as 1 over n, and the bias is just some order 1 constant. So sigma squared b and sigma squared w are just order 1. But this is done because if you remember, the next layer takes a sum over all these contributions. And so in order to keep all the signals to be order 1 as we iterate on this procedure, we put this 1 over n here to control that, to basically control that. But now thinking in terms of parameters is maybe not an ideal way of thinking about this problem for neural networks, because of the way that parameters are introduced into, parameterize the problem. So for example, neural networks have a lot of permutation symmetries in their hidden layers. So you can just do some permutation on the weights incoming to a layer and that go out and keep the function invariant, for example. So any description of the problem that is in parameter space or weight space has to take this into account, and you have to think about that a bit more. Whereas the thing that you really care about at the end of the day is not so much what the particular values of the parameters are, but what function they realize. So it would be nice to be able to translate statements about the parameters into statements about the function. And in this case, let's think about, let's consider translating the randomness we have on parameters into a randomness on F. Now, in general, if you try to tackle that problem, the distribution on F is complicated, but it turns out in this large N limit, it simplifies. So one way to see this is via the central limit theorem and making basically kind of a sequential argument where you take individual hidden layers to be infinite one at a time from the input to the output. And at every step, conditioned on the very inputs to the network, what you essentially do is you have some incoming signals, you multiply them with these random weights W, but there are infinitely many. So you can kind of see how you could view it as a sum over IID, infinitely many IID random variables, and apply CLT. So the result is that the distribution on functions F at the very end of the network or any intermediate layer Fs. So that's something I denote by F sub I with this superscript L, is given by essentially a Gaussian field theory, or in machine learning, it's known as a Gaussian process, but they're kind of morally the same thing. It turns out this, viewed as a field theory, it's a bit of a non-local one. So it's kind of structurally different, I would say, than typical field theories we might think about in physics. But another way to kind of restate what I'm saying is that there is a mean field theory here that becomes exact at infinite width, and at finite width is an approximation to the problem. So just to flesh that out in maybe more familiar language a bit more. So for this Gaussian field, again, just thinking about random at initialization, so random networks, for us in the setup that I described, the mean of F is 0, but a lot of interesting information is in this 2-point function, where I look at the covariance between F of X and F for some other input X prime. So think of X and X prime, these are inputs to the network, but later I'm going to take them to be drawn from my data set. And so this is encapsulated by this 2-point function K. If you want to think about it in kind of field theory language, this would be kind of the partition function that would generate correlation functions for F. And another, just to use other terminology that's often used in machine learning, this 2-point function is also called a kernel function. Kernels are, a kernel function or a covariance function for the Gaussian process. Now, because we have this recursion on the computations done by every layer computed, we have this sequence of Fs as we run through the network. This gives rise to some recursion on these Ks. Starting from the very beginning of the network, there's some K0 that describes the initial, the initial 2-point function. And as you propagate through, there's some final K that you get at the very end. So to be more explicit about it, for this vanilla setting again, if I want to calculate K at layer L, it's some function F in general of the covariances coming from the prior layer, KL minus 1. And you can, based on that recursion I wrote down earlier, you can write down a recursion for K really easily. And it's basically amounts to doing a 2D Gaussian integral involving where phi appears in the integrand. And so you can compute this either in closed form or numerically. And the initial condition is some 2-point function or covariance function that just involves an inner product between X and X prime. So it's just a Euclidean inner product, but as you propagate this through the network, it actually takes a very different nonlinear form. So that's kind of a summary of what this computation encapsulates. Let me just say as an aside before we talk about theoretical descriptions of learning, let me say some practical thing that you can get out of studying these maps, these 2-point functions. as a function of depth. So to be able to train a neural network at all, you have to make sure that it's initialized well, basically that it has some knowledge of the structure of the inputs x and x prime. And one practical problem in deep learning in the past had been that in order to train ultra deep networks, sometimes the networks are just too deep to train. So one thing that you can do is you can study the fixed points of this map K as you increase L. So the large depth, we took width to be infinite, but now we're going to take L to be infinite and look at the fixed points that it approaches. And in these vanilla networks, the fixed points themselves are pretty boring. Here we, in our work and many others before us, there are names to the phases. So here they're just labeled ordered and chaotic phases. These are some kind of boring fixed points, which you approach exponentially fast in depth. But there are regions of these basically like a phase space for the network. So this is now tuning these order one constants I mentioned at the very beginning that you also have a choice to tune. And in order to train a very deep network, the deeper you go, the closer you want to actually be to this line here, because that's where the convergence to a fixed point slows down and it goes as a power law. So if you imagine taking a 1D slice through this 2D phase space where I initialize networks with these parameters and I take a slice through here and I try to train them and see what happens, what you would observe is just that as you basically get closer to this line, the maximum depth for which you can train a network also increases.
Are those parameters the variances just for the first layer, or are they the same for all layers?
Here, they're the same for all layers. Yeah. So they're tied so that, I mean, you're repeating, you're studying the fixed points of this map, so there has to be some repetition as you go. But these red areas are regions where basically you can train well and the training accuracy is high. So a takeaway is one difficulty with training ultra deep networks in the past was that you really have to, if you want to go deeper, you really have to fine tune the system. So if you're just searching in this 2D kind of space, really you want to be around this line in order to train deep networks. And so if you use this knowledge from the theory to kind of initialize around these regions, you can train ultra deep networks without any tricks that you usually need in machine learning. Okay. So now let me just talk about actual learning a little bit. So one of the first frameworks we thought about for learning was a Bayesian one. And just to give a very fast, high-level overview of what that is, it's a probabilistic way of thinking about learning. So let's say you're given some data set D consisting of XY pairs that you want to fit with a model. When you think in a Bayesian way, you start with some prior over the parameters and conditioned on the data, after you have some data, you update that to some posterior distribution, which you then use to make a prediction. Now, typically, this requires performing a high-dimensional integral, d theta over all the parameters of the network, which for a large neural network is quite a lot. But you can actually change variables to do that integration in function space. So thinking of f as a field, f of x, and you're integrating over certain kinds of certain fields realized by the network. And it turns out that in this large N limit, you can compute this integral exactly because the problem becomes a Gaussian process. You essentially have a Gaussian field. And if you're furthermore using a quadratic cost function, so everything is Gaussian and you can just do the integrals. And the result is something as follows. If you want to get the prediction at some point x from the trained neural network, that itself is described by a Gaussian, and its mean and its variance can be written in this form, just based on that knowledge of the 2-point function that I mentioned earlier, realized by the deep neural network. So for example, to compute the mean, you take the targets y, and you take some particular linear combination of them weighted in this way by this 2-point function. So it has this form k inverse. And similarly for the variance. And so through this, you can analytically obtain exact Bayesian predictions from an infinitely wide deep neural network. Pictorially, you can think about it as follows. So in this probabilistic way, so before you do any training, you have this Gaussian field. These are samples from that Gaussian field. You haven't seen any data yet. And then after training on data, what you do is you essentially, if you don't have a lot of noise, you try to fit the values of f close to y, close to the values of those training data points y, but you haven't constrained the function f. You've only constrained it a little bit away from that. So you still have some mean prediction, which is this solid line, and some variance. And then these dashed lines show samples from that learned distribution. So the original Gaussian field, you can think of it as essentially a modified Gaussian random field where the field is now pinned near the values of the training points, but still has some fluctuations away from that. So this program, this kind of setup, which I described right now for the fully connected neural network, you can continue it for other types of the zoo of other neural networks that exist. And in each case, you want to try to find a parameter that is natural to take to large N. So in convolutional neural networks, that's the number of convolutional filters. In attention, for us, that was the number of attention heads that you have. There's a similar one for graph neural networks. And so you can kind of unify your thinking and you get a new method by basically working out and driving this correspondence for all these different types of architectures. And instead of thinking about all of the complexity of the architecture, you just have this 2-point function that you have to think about. So I kind of focused a bit more on this theoretical framing of it. I want to say it's also a practical method because many people in machine learning classically, especially for like more small scale problems, use Gaussian processes. So we also implemented kind of all of these Gaussian processes and compared them to finite size networks in terms of their prediction error and so on. And one of the things we found, just to summarize at a high level, was actually the prediction, the error that you get from the infinite network compared to the finite one varies quite a lot depending on both the amount of data that you have and the architectural class you're thinking about. So for example, for this kind of boring vanilla network, the fully connected network, the infinite width neural network or kernels do as well as the finite sized one. And it's only when you get to these richer architectures where you start to see more of a discrepancy. Any questions about this stage before? Okay, so in this part, let me now change the framing of the problem. So right up till now, I talked about a bit more of a probabilistic way of thinking about learning, which is this Bayesian framework. Now let's take look at the framework that's more common in practice now, which is that you just define a loss function and you run an optimization algorithm like gradient descent. And in principle, these are two very different ways of learning from data. They don't necessarily have to have a relationship with each other, but it turns out that they sort of do. So to be more precise, let's say you have this cost function, which I'm going to just take to be quadratic cost. So we have a quadratic function. F is our neural network with parameters theta that we want to learn. Y is the function we actually want to fit. And we want to solve for the minimum of this in parameter space. And we do this by running gradient descent with a particular step size eta that we have choice over if we're running this discrete time version of it, just as follows. So the question we want to ask about this in this large N limit is, again, what is theta as a function of time? And in particular, as time goes to infinity, so at the very end of training, and what is the learned function f? Can we say anything about that as well? Now, one way to state the results or what happens in this limit is to think about Taylor expansions of the network about initialization. So this neural network f, it's a function of x, the input, and it's time dependent because the parameters are time dependent. So you can think about the Taylor expansion of the neural network at any particular time as a Taylor expansion about the initial condition theta 0. So here we just have the initial condition, and these delta thetas are describing the deviation theta t minus theta 0, and we have all these, in principle, high order terms. But what ends up happening is actually in this large N limit, at any time during the optimization, the model essentially realizes exactly its first order Taylor expansion. So it behaves as though it just doesn't have these higher order terms. They vanish in the large N limit due to some dynamical reason. So the model that it does actually realize is one that is linear in theta. So that's captured by this delta theta term here, but it's still nonlinear in x because these gradients here it's still a nonlinear function of x. So hopefully it's clear that this is really a linear model, linear in theta, but still nonlinear in x. An equivalent way of describing this dynamics, which for right now I'm talking about in continuous time, turns out to be, and this was first highlighted in this paper, really nice paper by Jacote et al., which is to think about the evolution of the function f as just being described by this differential equation, which is linear. So f dot is just related to the error f minus y with this, again, what looks like what is a function of two arguments, this variable theta, big theta. And theta in this equation is just constant in time. In the literature, it has this name, neural tangent kernel. Question?
So, sorry, why is this irrelevant to time?
Relevant or irrelevant?
Irrelevant.
Why is this quantity?
Yeah.
So that's a non-trivial aspect of that is the claim of the that is the main claim. In general, it should be time dependent, and in this case, because of large N, it has no time dependence, and so it just takes on its value at initialization. So this quantity theta is so it's a good question. I can say more maybe towards the end of how it comes about, but it's something that emerges in large N that you have to actually work out.
There's like some dynamics that, maybe the fluctuation suppressed by 1/n.
Exactly. Yeah, it's exactly that. In this language, it's actually easier to see. And then this is sort of the dual or complementary language where you're thinking about the relationship between f and theta. So this description is sort of like a theta as in small theta, lowercase theta. The parameters does not formally appear here. So these are two kind of different but related ways of thinking about it. And this kernel theta, to define it, it's just this contraction over network gradients at initialization, so evaluated at theta naught, summed over all the parameters mu in the network, averaged over this ensemble of random networks. So it's averaged over this distribution that I described as n goes to infinity. And to compare it with K is just essentially the same expectation value, but using F instead of the gradient. And the reason gradients appear here and no gradients appear here is because this is describing gradient descent optimization, and this was describing a probabilistic framework where we didn't look at gradients. And similar to the recursion for K that I described, you can write one down for theta, again, leveraging this fact that you know that at every layer you have these Gaussian fields. And so you kind of just do induction on that to derive the recursion for theta. So with this linear differential equation, you can solve it exactly to get exact time evolution. And because this is not now a probabilistic framework, naturally, you can both write it down for a particular instance of a network, or you can then average over all the randomness that you have that originates from initialization to get the distribution. And this looks very familiar. It looks very similar to maybe the equations I showed in the Bayesian setting, except that here you're using theta to make a lot of the prediction. So again, you have this theta inverse appearing. You can also, if you look at numerics for a real neural network, which is the solid lines in these plots, and compare to this linearized model, by which I mean just a first order Taylor expansion, you see that there's good agreement out to early times, and at late times, like you see here, you start to see discrepancies. But the claim is that as you make the network wider, these discrepancies go to zero. And so you're exactly described by this linearized network. So just to summarize this section about dynamics at large N, in both settings, we had exactly solvable models. Just to contrast the two, for Bayesian inference, we were using, to make a prediction, we use this kernel K. And if we look at gradient descent training in large N, we have this kernel theta. Now, the fact that both were solvable and effective, this simplicity arose, really traces back to this initial scale that I talked about, where the weights have a variance 1 over n. So that controls both this side of the problem, and it controls it controls the dynamics as well. So it's not just something that affects the random networks. It has implications during the course of learning. And another kind of high level takeaway is that in this setting, although there are infinitely many parameters, the learn function is relatively simple. So it's not kind of an arbitrarily complex function f with a lot of oscillations or anything chaotic necessarily. It still can be a nice, smooth Gaussian field. You get Gaussian fields in both cases, but they have slightly different settings. They have these two different covariance functions that play a role. Now, to kind of transition or maybe back out how a more general way of thinking about this problem, which was not, it's not the way necessarily the problem was originally solved by either ourselves or Jaco et al., but I just want to frame it in this way because I think it's appealing. Going back to the equation for the dynamics, so let me just say, so in these equations that I'm writing down, theta is now, as was pointed out, it's a function of time. So it still involves this inner product between gradients of f at x and gradients of f at x prime, but it's time dependent because the parameters are. And let me just define R to be the residual error, which is also time dependent. But I'm just gonna, it's just something that appears in all the equations. It goes to zero, as time runs to infinity. But the more general set of equations that describes a system, if you want to transcribe to the set of variables, is that the evolution of f is described by theta, which is a function of two arguments. I kept calling it this 2-point function for the Gaussian that connects to this Gaussian field. If you look at the evolution, if you try to study the evolution of theta, it gives rise to this quantity that I'm calling theta 3, which is a function of 3 arguments, and so on. If you look at the evolution of theta 3, it's written down in terms of theta 4. And this has some kind of loose resemblance to the BBGKY hierarchy, if you recall in statistical mechanics, where we think of like the one body function, two body terms, three body, and so on. And this solution that I just described is basically solving the problem by truncating at this level and only solving this top problem, because all the other equations are suppressed due to the large N. But the real, more general problem that we have to solve is something that potentially involves many of these or all of these. So it's challenging to get a closed set of equations to describe neural networks in general. Now, I want to describe one way we found to actually close these equations in a very simple setting. And this simple, very toy setting remarkably has some predictions in it that we verified in real problems. So going back to what happens at large N, this solution that I described actually only holds, it was first studied for gradient flow, but really it only holds up to a particular value of the step size eta that you choose for gradient descent. And if you go to larger step sizes, as we found, you converge to a different part of the landscape and you get very different dynamics. So to see this, if you just analyze a single hidden layer neural network with no nonlinearity, so it's just this, it's just this combination of V dotted into U, which are the weights of the network. And if you even more simplify this problem to just consider a single data point, because it captures already a lot of the problem, you can go back and look at these equations that I wrote down for this particular problem. And you find actually that you can reduce it to a dynamical system that just has two variables in it. So these two variables are essentially f, a single scalar f, which is a function of time, and a single scalar lambda, which is a function of time. So f is essentially, in this problem, f is the loss is just f squared. So what we want is f just going to 0 at long times. And lambda is just, in general, it's the top eigenvalue of the NTK, of this kernel theta. But here that just reduces to, the matrix reduces to just a single scalar. So we have two variables here, f and theta. And what controls this dynamical system is also the choice of the hidden layer with n and the step size eta. So if we look at the fixed points of this system at long times, what you find is actually that this, if you're at an eta that's less than a critical value, which is just 2 over lambda naught, the long time dynamics essentially goes to this solution that I described, where we have these constant kernels, big theta. And if you take eta too large, optimization diverges, but there's some sweet spot in between, which is of finite size. So this C is usually some constant. In this problem, it's just 4, but it's just some constant. In this sweet spot, you actually get very different behavior. So the kind of pictorially, the picture you should have is that what happens here is that very early on in training, you catapult out of the local basin that you're in, but you manage to converge in some other basin. And typically that other basin is flatter, and it has a lower value of lambda. In contrast to what this other solution that I described, where you essentially just explore the local basin around you that's close to at initialization. So you can kind of think about it as the difference being, in one case you go to the basin kind of close to you, and the other you just catapult out somewhere else into the landscape early on in time due to the choice of learning rate. Just to drive home this point a little bit more. So this dynamical system has sharply different fixed points as a function of eta. And so what kind of plays the role of an order parameter here is this change in theta during the course of training as you take n to infinity. So in this first regime that I talked about, so everything to the left of the blue line, this change in theta goes to 0 as you make networks wider. So this is getting wider and wider from black to red. But in this other regime, so essentially to the left, to the right of the blue line and before the pink line, you get a change in theta that is actually order 1 during the course of training, doesn't change substantially as you take n to infinity. So there's a sharp distinction between these two at large n that we can actually get out of this model just by looking at this simple dynamical system. There are other things we can get out of it, like notions of critical exponents and so on. And if you want to read more, actually others in the physics community have been working on this model as well, it's been used in other places to try to get some insight into just the dynamics of optimization as well. Maybe just to summarize a bit of this section, if you'd like to read more about some of what I talked about kind of at a pedagogical level, I have some lecture notes from some lectures I gave at Les Ouches on this topic. And right now I'm working a bit more on trying to push these models into to study other models that have feature learning. So where this big theta 2-point function still evolves in time. And I'll just say in passing that one of the things that one of the techniques that people use in this area, kind of in this intersection of physics and machine learning, is often taking techniques from the physics of disordered systems, where you think of the data as essentially your disorder. And what you would like to do is look at the error after learning averaged over your particular draw of data. So you have a particular training set that you draw of finite size from your data distribution, but really you would like to maybe understand kind of averaged behavior. And so that's sort of the link between the two, where data is often viewed as disorder and we average over that. So that's just to maybe mention that connection with some of the techniques used for disordered problems. How much time do I have? Actually, am I doing okay?
Yeah, maybe for another 10 minutes.
Okay, great, thanks. So these were different types of models of learning, both exact solutions and other things that are not fully exact solutions or general purpose, but they still have some insight. I want to now talk about an application where, because we have now like a closed a solution we can write down for what happens after learning, we can analyze that to look at the scaling of error as a function of basic variables in the problem. So one thing that in general in machine learning or any kind of algorithm really is you want to look at the error, how the error scales with the size of the problem, which in our case, two variables that are of interest is amount of training data and the size of the model, so the number of parameters. So this is like the sample complexity, and I'll refer to this other thing as essentially the parameter complexity. So in recent years, people have started to look a lot empirically at what what the error or the loss looks like as you scale up the problem. And they have used it, basically measurements of this, to figure out the smartest way to basically scale up a neural network where you get the best loss for the budget that you have. So that's more a practical thing, but kind of distilling a theoretical problem out of that, we'd like to understand how the test loss behaves as a function of the amount of data and the number of parameters. And empirically, it's usually observed to be a power law sort of relatively clean power laws in at least some number of experiments. So this loss has some constant term, and power law behavior is a function of D and N, the data set size and the neural network width. And it would be nice to be able to say something about this form. In particular, how does it depend on the data and the architecture? Are there regimes with universal behavior? And so on. And so in our work, we can't analyze we can't analyze the full form of this, but we can say certain things about the exponents alpha D and alpha W. And we do this by starting from a simple theory setting and then trying to extrapolate to real networks. Just to maybe summarize this, and then I'll kind of jump to the conclusions, I think. On the theory side, something that is very commonly studied in these settings is a student-teacher framework, where there's you have to assume something about how the data is generated for your problem. So you assume that it's generated by some teacher neural network that produces some data, and then there's a student neural network that learns from that. But now we can use these new solvable models, these kernels that I mentioned that you get in the large N limit to look at this problem. And we look at different regimes, both asymptotically, where either D is large or N is large, and different ways of scaling. And the high-level summary is that there are regimes where you just get universal exponents equal to 1, which is essentially coming from kind of fluctuations about a nice limit where you can expand. And then there are other regimes where the exponent is very data and model dependent, but it depends on those those things through some other quantity, which in this case is the exponent of that you see in the eigenvalue spectrum of the kernel. So going back to these kernels, either K or theta, if you look at them on real data, after some transient regime, so these are, you'll see that the eigenvalues, lambda I, start to look like power laws. And they roughly have, this form, power law in the index here with some exponent alpha K, 1 plus alpha K. And that exponent is related then to the exponent that you get for data or model size scaling. And as you change the complexity of the problem, so here we have images, but we're coarse graining them to tune from, between these different curves, you see different values of alpha K. So really the data itself has some structure. As it's pushed through the network, that structure changes in a way that's architecture dependent, but it's encapsulated all together in this kernel spectrum, because the kernel here is that relevant quantity. So anyway, with that, we can, there are some aspects of this, so we get this out of the theory, and then there are aspects of this that hold up in a more general setting outside of this large N setting, where you have actually featured neural networks that do feature learning. So just to
quick question, why is there no depth dependence in this?
Why is there no depth dependence? There can be. It's hidden in alpha K. So here, this is like a fixed network, a fixed depth network. And we're changing the input data, but if you change the depth, you would also change alpha K, and therefore change the exponents.
In some other contexts, what one sees is I know it's not the same eigenvalue spectrum, but a power law and then a transition to a random matrix spectrum. Do you expect to see that as well?
So maybe that's connected to here. These are kind of the asymptotic the asymptotic behavior of the spectrum. But if you have like a finite size, or you introduce other dimensions into the problem, you can sometimes here you see power law and then it just kind of truncates and the tail behavior is different. It's probably more, those random kind of universal classes of random matrices. Okay, so just I won't walk through all of the remaining slides, but just to say that that was simple theory, theory in a simple setting where we can work things out exactly. Some of it holds up in realistic networks. So if you look at just real neural networks, there are these regimes where you see the exponents 1, and these other regimes where the exponent is very data dependent. But here we don't have a control over what the final kernel is, so we can't exactly say, connect that to the exponent. I'll skip this. These are other predictions from the theory that we see in other regimes in ML, in kind of like pre-training fine-tuning regimes. I want to maybe just wrap up and summarize some high-level things. So what I talked about at the beginning, these connections to Gaussian fields and kernels, actually, as a method, it turned out to give rise to state-of-the-art Gaussian processes and kernels, just because they're derived from neural networks and they have that richness and compositionality and also non-locality. So a lot of classical older kernels maybe were, very local, and neural networks are actually, give rise to these non-local kernels that are perhaps more powerful. These solvable models, they helped lay some foundations for deep learning theory and revised existing wisdom about what happens when you have lots of parameters in your learning problem. I think this kernel view on learning, where the kernel is some dynamical object, is a useful one on learning. So you can numerically study a lot about neural network learning by looking at that quantity. And also, I think this language of correlation functions in general that appears very prominently at large N is also just a useful way to think about neural networks, because you essentially have marginalized out the contributions of the parameters. You don't have these, we don't talk about specific parameters, but just about, what happens in function space. Since our work, there's been a lot of other developments in different directions. So you can do perturbation theory around large N using techniques from field theory. You can study other large N limits where you scale, you don't have this 1/n scaling in the variance of the weights that I mentioned. And this gives rise to, more challenging problems that are interacting, and there's been some applications of kind of techniques from dynamical mean field theory to think about that problem. And it also just highlighted the importance of how you parameterize the network and how that controls the dynamics, and has gotten people to think about kind of having invariance in this parameterization as you scale networks up. I would say that to date, it's maybe one of the strongest general purpose theoretical handles we have on deep learning, because a lot of other theory is either typically, unfortunately, problem dependent. Like you'll study a problem with some number of layers, some very specific assumption on the data and so on, or it naively involves too many variables that don't kind of help you gain more insight. I want to say that some of these results and ideas have also been used in various parts of the sciences. So for example, a recent, an area that's gotten a lot of interest is trying to develop learning theory for quantum many-body systems, and in particular, trying to get algorithmic guarantees when you train neural networks on data from some quantum measurements. So for example, maybe you use this classical shadows, the shadows formalism to make measurements in a quantum experiment, and then you'll train some predictor on top of that from your data. If you want to use a neural network for that part, then if you want to have some guarantees on the error, you need to know something about neural networks. And these solvable models were used there to get some of these first guarantees when you learn from data in quantum experiments. These ideas kind of conceptually that I alluded to, where we have either lazy learning or rich learning, where we converge the solution essentially converges to a nearby basin or goes into some other basin have also made their way into theoretical neuroscience. And people now thinking about biological neural networks kind of through this lens. Okay, I think maybe I'll just end there. That's all I have prepared. And thank you for your attention and also the invitation again.
Is there any question?
Anyone else? No.
Yeah, I've got a question. So you, in the first part of your talk, you described how you could use these 2-point functions as a way to sort of compare different kind of network architectures. Could you just maybe elaborate on that? I mean, I understand it conceptually, but how might you use that correspondence?
So one of the ways is if you look at something that is clear from the solution that you write down, and also you can formulate some metrics, precise metrics out of this, is how well, say, the kernel eigenvector, the kernel. So what matters in that solution is the eigenvalue spectrum and the eigenvectors of the kernel when you evaluate it on real data. And in general, the better aligned your target vector is. So these y's, if you think of it as a vector, when it's aligned very well with the eigenvectors of the kernel, in general, that's a better starting model, for that learning problem, because it's already captured by the kernel eigenvector. So that's, for example, one way that you can use that. And better architectures will tend to have better alignment.
Okay, thank you.
I'm curious about maybe at the end of your second part, you mentioned that there's a connection between your model of learning process and maybe disorder system, and you said by mapping these problems into disorder system, you can gain more insights. I'm just a little bit curious, for example, whether like after mapping, there are some phase transitions inside the disorder system, like localization, like these kind of things, how they are related to the actual learning process. Do they tell you something about maybe how, like, which phase of learning you are, because you show like kind of a one-dimensional phase diagram that.
Yeah.
Thank you.
I missed the last part. Can you say?
Oh, I just said whether the mapping to disorder system will give you a phase diagram that better understand that the phase diagram that you're currently showing, that one-dimensional phase diagram for a simple learning problem. Yeah,
it helps you get a phase diagram for your notion of phase. It's the notion of phase would be, for example, just looking at the error as a function of the so going connected to these scaling laws. So the error as a function of the amount of data that you have or other parameters that you're tuning. Yes, people do find phase transitions, transitions between different regimes for this problem. So yeah, definitely. I don't know that they've used kind of connections to localization that much in it. Maybe that's just something that I don't know too much about. But they use it to primarily calculate the error, because the error. So it's like the error is dependent on the data set, so the data distribution and the amount of data, but you would like to average over the particular draw of data that you have, or maybe you want to average over other things like the initialization. So any kind of randomness you might want to average over. You still have to make some assumptions or put more in terms of what predictor you're using. So it's not necessarily helping you solve the learning problem. For example, I described these exact solutions. For that, you kind of had to study the dynamics as a function of time or map to these Gaussian fields. But it does, once you have that predictor, so you know what the function f is after learning, or something about the weights, then you can use this connection to disorder and use techniques from like replica theory to average over that. that's sort of a area other physicists have also worked on a lot historically in the past few decades.
Okay, thank you.
One very quick question, which is binary. You mentioned, your Zeus lectures are available. I'm wondering if this PNAS paper is also available.
It is on archive, but not the version. It needs to be updated. So the PNAS version I will update soon.
Okay, and then the last question is, in the beginning, you made a tantalizing remark about how some rigorous mathematical theorems turned out to, mislead in practice some training. What is an example of that?
So one I think is just notions about the global optimization landscape. So for example, there was more of an older view that the optimization landscape would have a lot of minima at high values of the loss, or all throughout kind of the as you tune the loss or the energy of this cost function. And then it was really, I think, work really spearheaded by actually Surya Ganguly, I think, that kind of brought this idea of actually saddle points are the thing that dominate maybe in high dimensions and also for these kinds of landscapes. So that was something that then kind of changed wisdom, I think, just by looking at, other kinds of random landscapes, although I think that there are still open questions around that in terms of how the data gives rise to the landscape and so on. Another one was just, like other, this large N limit could have been maybe solved a while back. But I think there was this prevailing view from maybe a lot of rigorous theory that in general, as you increase the number of parameters, you're just going to overfit. That's like the classical statistical view from statistics that I think holds for other parametric models, but maybe was not quite right for neural networks, or at least empirically has kind of been disproven for neural networks. So those are maybe two examples.
It sounds like they may have been rigorous, but based on the wrong premises.
Yeah.
Great.
So in the Gaussian field theory, you argue that the phase transition between the ordered and chaotic phase corresponds to successful learning. Like polynomial, the parallel correlations corresponds to successful learning. So what's the physical intuition behind that?
Yeah, it's not it's just that so learning, I should say training, so that you can train deeper networks. Like away from, so the approach to the fixed point is exponential in depth in those two other, the ordered and chaotic regimed, which means that essentially when your network, so that's like there's a correlation length associated with that. Let's say, so how rapidly that, the length scale of that exponential. And so the depth of your network compared to that length scale is what controls whether you have enough signal information about the input to train or not. For this power law decay, that length scale essentially goes to infinity. And so, you can train ultra deep networks. There's no like cutoff scale. That's sort of the high level, maybe, intuition. But it's just to flesh that out a little bit more, heuristically, what you need is, in order to train, you need some information about the inputs to reach the end of the network, because you do back propagation. And so the more structure of between, you have about, the overlap between X and X prime, that's useful for learning. But if you're approaching this fixed point, you've lost that structure and it's kind of all uniform. It doesn't, it loses the information in the data essentially. Did I maybe answer that question? Well,
Yeah, I think it makes sense that there's a length scale that comes into play.
Okay, if there are no more questions, let's thank Jessamine again.
Yeah, thank you.
Literally, that's the exact same thing.